This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Which input do we want to output at a particular location, or at the output, I should say. And what we did is we showed that this one way that you can actually implement a multiplexer is by a number or two transmission gates. Now, of course, just to repeat myself again, multiplexers, using transmission gates means that they're non-restoring. That's not the best way of doing it. It will work, but it's not ideal. But notwithstanding that, this gives us a way of being able to build a multiplexer, right? We then, I showed you very briefly how to build a tri-state buffer, which was essentially, restoring our multiplexer using these tri-state buffers, and we've shown you how to develop or build those kind of circuits. Right, and then what we went on to then was to talk about combinatorial and sequential circuits, and we said that, for a lot of us, we've seen combinatorial circuits, time and time again. We've started using them from, first year potentially, where we've got sequences of ands and ors and whatever, and we build complex circuits. But there are some disadvantages of doing that. Can someone tell me what the disadvantage of just building large asynchronous circuits would be? What are some of the challenges?
To compute the propagating delay.
Yeah, it's hard to control the propagation delay, right? Because it's state dependent, and usually if you've got very large circuits, it's generally very difficult to know what is happening at a particular location, on the chip or in your circuit at a particular time. So usually what you do is, yes, you still build combinatorial circuits, but usually you put them between sequential circuits or things that actually sample the output. Okay, and on that note, what we started to talk about was we introduced two concepts which you've thankfully have seen before. One was a latch, and we said a latch was what kind of device? It's sequential, but how does it differ to a flip-flop? It's level sensitive, right? Whereas flip-flops are edge-triggered devices, right? And then what we did is we went through and showed you what, how to implement a D flip-flop. Okay, and then what we said was essentially what is happening when we're implementing a D flip-flop is we're actually sampling the output at a particular moment in time, right? So irrespective of what's happening in between, we don't really care. If the outputs are actually changing, we don't really care, because the only thing that will happen is we will sample the output at either the rising or falling edge of that clock, depending on how you've implemented that flip-flop. And essentially what I'm saying is if it's a positive edge flip-flop, it will trigger on you will sample on the positive going edge, and if it's a negative negative edge flip-flop, you'll sample on the falling edge. Okay. Can someone tell me, we're going to talk about propagation delay. I made a statement and nobody challenged me. So let me ask, how are these flip-flops going to help us? I said, we don't want to do, we don't want to build large asynchronous circuits. Now, I've got to back away a little bit from that, because one of the things that people are doing now is trying to build these large asynchronous processes just so that they can make them run a little bit faster than your traditional architectures. But let's assume that still remains in the realm of research, because they're very researchy type devices. What are the advantages, or how do these flip-flops help us in the design of fast digital circuits? How would they help us? Yes?
Well, if we can control the clock then we can basically control the delay, the frequency at which the information is transmitted?
Sure. So essentially what we do is we sample and hold that information between two points in the circuit. And what that allows us to do is to actually say, well, if we make those circuits small enough and we've got a little bit of flexibility with the clock, we can actually start trying to design these circuits so therefore the propagation delay so that that circuit processes the input signal, and I'm talking about the asynchronous circuit, processes that input signal so we get an output at the input of the flip-flop, so that when the clock arrives we sample it and we know that we have a known good stable signal. Okay, excellent. All right, so now let's start talking about delay in digital circuits. Okay. All right, so as you can imagine, we're going to start by looking at some very simple circuits, right? And, you know, one of the things that I apologise. I don't know how to focus this. Anyway, one of the things that we're going to focus on is, you know, the inverter. That's usually one of our go-to circuits. It gives us a lot of insights. So what we're going to do in this part of the in this lecture, I should say, is focus on some simple circuits in order to get us to understand what causes propagation delay. All right, and what causes the delay through some of these circuits, which are acting as digital logic switches or circuits. Now, the first thing that I wanted to talk about is propagation delay, or some of the definitions. So here, what I'm showing is an input pulse, right? So essentially what we've got is a signal that's coming in. Suppose that the signal was initially, or the circuit was initially at 0 volts, and all of a sudden we start seeing that the voltage begins to increase, reaches some maximum, and then decreases again. Essentially what we're saying is we've got some kind of pulse, some clock pulse, right? And you might say, well, why is that rounded, right? Other than usually I can't draw. In this case, it's specifically designed to be a little bit rounded. And what we'll see in some of these circuits that we analyse is that's important, because what it's actually saying to us, or what we will do as part of this analysis, is if you don't have a perfectly sharp edge where this rise time is infinitely small, what happens is, even in an inverter, you actually go through another step. There's another stage of operation, or essentially another mode of operation that you need to consider. And we'll go through that in a little bit more detail. But essentially here, what we've got is we've got a pulse, it's increasing. And the first thing that I wanted to look at, and as you can tell, this is an inverter type structure. We define the propagation delay as the time that it takes from the time it takes from the input going to 50% of VDD to the output dropping to 50% of VDD. That's a propagation delay. Right? That's the definition of propagation delay. Now, there's also a definition of something called contamination delay. Who's actually heard of contamination delay? Okay, good. Essentially what that says is, when we're working out the propagation delay, it's usually the largest. When we say propagation delay, we're usually referring to the largest amount of time it takes between the input going to 50% and the output hitting 50%. But also you can think of situations where what's the minimum time for which that happens, right? So it's the same thing, but instead of looking at the maximum, you're looking at the minimum for which that occurs, right? And it depends, and you can, under certain circumstances, what you'll see is, depending on how you've sized your transistors and the like, because you've got, complementary pairs, you've got a PMOS or an NMOS, what you might find is that the propagation delay is critically dependent on if you're going from a 0 to a 1 transition or a 1 to a 0 transition, and the 0 to 1 transition might be a lot smaller than the 0 to 1 transition, as an example, right? There's no reason why those two transitions, 0 to 1 and 1 to 0, from going, increasing your voltage to decreasing your voltage at the output, need to be the same. Okay. So we also then talk about rise time. Can anyone tell me what they think rise time is? Sorry. There's something wrong with this, but anyway. So, okay, rise time.
It's the time that the flip-flop holds the value?
Sorry?
The time, like the duration the flip-flop takes to hold the value?
Or so it's essentially, if we look at this point here, it's from the time that it goes from 0 to go to 50%. Right, so we're actually, how fast does it rise, the signal rise? And likewise, fall time, sorry, it's from 20% to 80%, sorry, rather than 50%, yes. So, yes, it's how fast does it rise and how fast does this signal actually fall from 80% to 20%, and then we also define edge rate, right, which is the mean between the rise and fall times. At the moment, we're not doing anything special. These are all just definitions, right? So, as far as you're concerned, you just have to be like, okay, this is what propagation delay is, this is what contamination delay is, this is rise time, this is fall time. That's all it is. So far, we're only talking about definitions. Now, what we're going to do now is we're going to talk about, we want to make, the focus of this lecture series is on high-speed electronics, right? So one of the things that we'll always want to do is make our electronics, of course, go faster, right? Now, one of the things that I wanted to point out to you is that at the moment, this course is going to be focused a lot on the last three components, which is logic, schematic optimizations, potentially circuit level optimizations, and a little bit about layout type of optimizations. But to be completely honest, right, the best way to improve the speed of your system is, and the most gain is from an architectural point of view, right?
And how is the architectural different from the layouts?
Okay, architectural is, think of the following situation, right? Suppose I said to you, work out a Fourier transform. Build me a circuit to build me a Fourier transform, right? And you can say to me, okay, I will implement a discrete Fourier transform. I'll implement it how I would implement it when I do my mathematics. When I do my second year mathematics, I'll implement it as sums and multiplications, and etc. If you do it that way, okay, so you do it that way, right? And then you can focus on making the ands and the ors a little bit faster. You can focus on making the multipliers faster, and maybe you'll get it 30% faster, all right? But if you realize that, hey, if I implemented this, if I want to do a Fourier transform and I implement it as a fast Fourier transform, right, in terms of using butterflies and multipliers and reusing all those components, I can get it probably a factor of 1,000 faster, right? Because what you're doing there is the architecture itself, the way that you're doing the calculations are different.
Like the original ID.
Sorry?
The original ID different.
Yes, absolutely, right? So what I'm saying here is, even though we're focusing on this is what you get, 20% benefit, right? So, for example, if we knew that we were going to implement an FFT, I said do a DFT, you knew that you were going to implement an FFT, then what we would then do is say, okay, we know that we have to implement an FFT, now let's use the technique Stan is teaching us in order to improve the performance by an additional 20%. But if you'd implement it as a DFT, and you did all this hard work and you got 20% improvement, or you opened up a book and looked at, you know, how to architect a DFT or how to do a Fourier transform more appropriately as an FFT, you will get 1,000 times improvement, right? So that's where most of your benefits is really going to lie, right? So what I would strongly suggest is when you're doing your design, spend most of your time on the architecture and find the most efficient way to actually implement the function that you're trying to do, right? Then you can look at second order, potentially second order effects where you're looking at, you know, how do I make these specific circuits a little bit better, okay? So have you, I guess you guys have done some Verilog or VHDL design, is that correct? So what kind of things did you do in that course? Sorry? So addition, subtraction, multiplication. All right, so how did you implement the multiplier? Okay. So I guess what you did is you said multiply and the synthesizer just gave you something and you were like, all right, cool. Now, that's where you can actually get benefits, right? Because depending on what the synthesizer does, right, and what circuit it actually instantiates in order to implement that multiplier, you can get very significant, you know, differences in the overall performance, right? At the moment, I don't know, you don't know how the synthesizer, what kind of circuit it actually, or architecture actually used to implement that multiplication, right? And usually, for all of you that are passionate about FPGA design, your colleague who wasn't here that was wanting to do FPGA design when he went back home, what you would do when you were doing, if you were doing that in an FPGA, is you wouldn't actually use the multiplication symbol. What you would do is you would instantiate a multiplier from, you know, Xilinx or Altera. I think Altera is Intel now. So from the Intel library, which implemented a multiplier, which would probably be 100, if not 1,000 times faster. Right? Now you can say to me, Stan, I'm only implementing a calculator. I can only put the numbers in so fast anyway, and if it takes 1 microsecond, or it takes 10 microseconds, or it takes 5 nanoseconds, I really don't care because I can only put numbers in at, you know, 1 second, right? So therefore I will say, fair enough, guys, good, right? Yes, you don't have to do extra work. But if you were looking at, you know, for example, you know, looking at very fast modems where you're transmitting data at 5 gigabits per second, or things like that, that's when you start looking at, hey, what do I need to do in terms of my architecture in order to get the appropriate performance? Anyway, so I'm not trying to convince you to ignore me. All I'm just trying to be is a little bit honest so that you know, if you're doing the design, you know where to spend most of your effort. Okay, so now let's talk a little bit about transient responses. Okay, and so the first thing I wanted to talk about is this simple capacitor, right? And you know, if you look at this capacitor, I'm sure you've seen this formula, which is Q equals CV. So therefore, the charge that's stored on this capacitor is the capacitance times the voltage of that capacitor. And then essentially what we can do is we can then relate that, we can actually use that to derive the current, right? Now, you've probably seen this as I equals S omega, you know, V, right? So that's how you've seen it. But this, essentially all this is doing is we're saying we're differentiating this quantity with time. With, the rate of change of charge is actually current. I'm assuming the capacitance doesn't change with time, and the only thing that remains is C dV dt. Now, the truth of the matter is, when you've got a PN junction or a transistor, as you're actually changing the voltage, you're also changing its capacitance. So technically, this isn't true, but for first order approximation, it's good enough for what we're trying to do in this course. Okay, so let's now look at these two inverters, right? So essentially what... This is annoying me that it's not focused. Anyway, we've got two inverters, right? And what we're going to do is we're going to have one inverter driving a second inverter through a piece of wire. And now what we want to do in order to be able to start looking and determining the propagation delay is let's start looking at all the capacitances that live or appear or are part of this circuit, right? So here it actually hides a lot of detail. If I'm actually drawing it as this schematic diagram, it's hiding a lot of these capacitances that are really living there and are causing our circuit to decrease in speed and increasing our propagation delay. So let's now look at these two transistors. So we've got a P and an N type. Can anyone remind me, why didn't I put an N? Why should we never build an inverter N and then P? Why do we always build a P and then N? Yes, perfect, good. All right, good. All right, so you're paying attention, yes.
What was it, sorry?
All right, I mentioned that in last week's lecture. Okay, sorry, yes, on Wednesday's lecture. Essentially, an NMOS device is not good at passing a 1. It's got it's a weak passer of the 1 signal. It doesn't act as a good. It's good at an NMOS transistor is good at shorting an output to ground, but because it's got a finer impedance, when you're actually trying to push a 1, it's got a large resistance, so therefore potentially got a large resistance, so therefore it's hard to keep that voltage at 1. All right. So what we've done here is I've essentially gone through and drawn all the capacitances, right? So there's a couple of capacitances. So here what I'm actually drawing are all the capacitances as they relate to the source and drain relative to the base, right, or to the substrate. And again, since I don't like putting a second S because it confuses everything, what I'm doing is working out the capacitance from the source to the base for the P-type device, the capacitance of the drain to the base for the P-type device, the capacitance of the drain to the base for the N-type, capacitance of the source to the base for the N-type. Then I have this capacitance of this wire. Why does this wire have capacitance? It's got, I've put a shunt capacitance, yeah, but where does this capacitance come from?
The layer in the transmission line.
Okay, so you can think of it as a transmission line or a piece of wire, and essentially what this piece of wire is over, some ground plane, or and consequently, if you're doing that, that has some capacitance, right? Okay, so we've got the wire capacitance. And then I've got these two other capacitances. Can someone tell me what these other two capacitances are? Where do they come from? Okay, yes, I've written that there. All right, yeah, so there are two gate capacitances, right? So I've got the capacitance of the gate of the PMOS device, the second PMOS device, and the capacitance of the N-type device. Now, okay, sorry, you've got the lecture notes. I can't do this trick. All right. Now, I'm going to say to you, ignore these two capacitances, right, in our calculation. Why? So when I'm switching, why can I ignore these two capacitances? Does the voltage at this point change? No. So therefore, since I'm not charging or discharging it, I can ignore it, right? It's not doing anything. It's not actually adding anything to my circuit, right? Now it has some advantages, or it might also have some disadvantages. But yes, it doesn't add to the propagation delay. So essentially what I'm able to do is we can actually remove these two as part of when I'm doing the calculation. So when I'm looking or calculating the total capacitance of this circuit, what I've got is the total capacitance that this output node sees, or this circuit sees, I should say, is essentially these two, that, and this output node also sees that, plus that, plus that, plus that. So therefore, our total output capacitance is written by the summation of these components. Move it up? Yes. Yes. Okay. All right. So that's our total capacitance. Okay? And if you were looking at the layout, so let me just ask a different question, just to make sure that you guys have got the right intuition here. If I wanted to reduce capacitance, what do you think some of the easiest things to do would be? Suppose I didn't have much choice in the substrate or the diffusion capacitance, right? Because the diffusion capacitance, it's really, in many cases, it's hard to change because you're looking at the size of the N tub in the P well, right? So that's a little bit hard to modify, especially if you've got a particular process. But the ones that you can actually change and play around with is the wire, of course, and you can have two things there that you can play. You can try to make the wire shorter, or if you're doing it on a chip. Now the question is, I don't know if you're familiar with chip design. If you were doing it on a PCB board, what would you do? So if you had a ground plane, would you put the wire closer to the ground plane or further away from the ground plane in order to reduce the capacitance? Sorry? Okay, so let me do this. Let me write this. So that's area. And this is D. What would I do if I wanted to reduce the capacitance? Increase the distance, right? All right, cool. So they're the kinds of options that you can do, right? Now, the problem is, if you increase the distance, you need to go, if you're doing it on a chip, you have to go through multiple vias, and then you've got to worry that you've got to, the vias are sufficiently large so that you don't add a ton of inductance. And then also the other problem that you face, at least on the chip, is that as you go higher in distance, higher in layer, especially in the back end of line layers, they usually, the minimum feature size becomes quite large. So usually, I think on the 65 nanometer Samsung process, what is it? 50 micron is the minimum.
To do what? Sorry.
The top layer, the RF layer.
Width. I don't know.
Okay, but usually it's quite large, right? And therefore, so you got a bit of a trade-off, right? Anyway, so this just gives you a little bit of an insight. Play around with the wire, and then also you'd want the size of the gates to be as small as possible that you're actually driving. But the problem there, why shouldn't I always choose the minimum gates size? You can see it from you can even see it from this circuit. Why wouldn't I choose the minimum gate size if I wanted to go faster? Right, I've got two things that I'm worried about, right? One is the capacitance, but if I want to charge the capacitance, I need what? High drive strength, right? And the drive strength depends on the width of that transistor, right? It's W10l. Remember, current equals W10l times VGS minus VT all squared, right? And there's another constant in front of it. So there's a trade-off between the capacitance and then also your drive strength in the amount of current that you can actually generate in order to be able to charge these capacitors quickly enough. Okay. Now, let's now look at this situation. So what I've done is I've rewritten this circuit with just an equivalent output capacitance. And what I'm going to assume is, at least initially, I'm going to assume an infinitely sharp edge, right? And the reason why I'm doing that is so that in this particular case, I'm only going to look at 2 areas rather than 3, and then we'll talk about the 3 areas later on. Okay, the 3 modes of operation. Okay, so let's now look at this, right? So therefore, when the voltage step is applied, right? Initially we're at 0, so N1 is off, P1 is on, and B here is VDD, right? And so let's assume that this has been on there for a very long time and this capacitor has been charged to the out, right? What happens when I apply a 1 voltage? Right? So when I apply 1 voltage, P1 starts to switch off, and if it's sharp as I've got it here, P1 switches off almost instantaneously. Now N1 goes through 2 regions, right? And what it's essentially what N1 is being used for is actually for this current to go somewhere and actually discharge this capacitor, right? So an N1, depending on the voltage at this point, is either going to be in saturation or the linear region, right? So initially we're going to be in saturation, and then what's going to happen as we get as the node B falls below VDD minus VT, this will go into the linear region. So let's now do a little bit of analysis. So we know when we're in saturation, we know what the current is, right? And we know how to write the current in terms of VDD and VT. So therefore, let's do that. So therefore, dV dt is equal to some constant beta on C out times, this term which gives us the current when we're in saturation. And this is what happens when VB is less than VD minus VT, we now go into the linear region. And if you do the analysis, even for a sharp transition here, or a sharp step input, what you start seeing is that your voltage, at the input, at the output, you start getting a decrease. So this is when so this is where the, I should make that T0. You've got your voltage, and then all of a sudden it begins to die out, right? So initially it dies off linearly, right, in this region, because this doesn't depend on VB, right? So linearly, then once it goes into the linear region, you've got it depending on VB. It's a nonlinear equation, and you've got this decaying type of relationship. Now, the thing that's important here is that what we're doing, what we'll be doing as part of this analysis, is we're going to be approximating this nonlinear decay by an RC decay model. It's not technically 100% correct, but for engineering purposes and in order to be able to get some insights, it's close enough for what I call government work, so that it allows us to get some insights on what's going to actually happen, how this voltage is actually going to decay with time in order to go from a state, this being voltage 1, to it being voltage 0. And also, what it highlights to us is that if we want to go from voltage 0, from voltage output 0 to voltage output 1, the NMOS transistor is the most critical, or plays the most dominant role. Now the question I've got is, how about if you're going from 0 to 1? What controls or dominates the dynamics of the output? If it's not the NMOS, it must be the PMOS. Okay, excellent. All right.
Sorry.
Yeah.
Why is the graph at the bottom? Why does it start off in state 0?
No. I've said t equals 0 here. It should be. It should be.
Should be 1 of
Yeah.
them.
Yes.
Right, okay. I thought I was missing something.
No. Okay, so let's go t equals pulse here. All right, good. Okay, so as Will just pointed out, I had done this, which is incorrect, because time equals up, and this is time equals 0, so the voltage is at 1, or VDD. We switch, and then this is what happens to the output voltage. This is how it's decaying down to 0. This is a problem when you don't copy out of the book. Now, just for everyone's benefit, the book that I like to use for all of this stuff, it's called VLSI Design Principles by Neil Westy, and I'll send it to everyone, right? So it's a great book, and I would recommend that you have a copy or find a copy online or something, right? So, all right, let's now look at. And Neil West is Australian, so we should really be supporting him, right? So that's the other thing. So now let's consider the this inverter, and essentially what I'm going through now is what happens when we don't have a sharp edge, right? So let's now assume that the input A, right, is from another gate. Right, and essentially it has a finite rise time. What actually happens? And here what I'm trying to highlight is essentially that there are 3 modes or 3 components to the output. Now in phase 1, as we said, N1 is off, P1 is on, B is at VDD. We then go to phase 2, up to phase 2. P1 is on. Now, in this particular case, what we've got is when the input is greater than when it gets larger than the threshold voltage, what we've got is P1 is on, N1 is on, right? So what we've got in this particular case is current is actually being received or transmitted, or whatever the right terminology is, both through the PMOS device, but also there's current which is being discharged through this capacitor, right? So essentially what we're seeing in this, when the output is, the input is, the input is in this region, we've got the PMOS device and the NMOS device are actually, to an extent, opposing each other, and that actually slows down the response. Now, as the input voltage increases, what happens is the PMOS device switches off, and then we've only got the NMOS device, and that's where the analysis that we were looking at previously. Right. So therefore, these are important things to realise, because what it does is it actually helps you understand, how to optimise, the circuit and the size of each of these components of these transistors in order to get some desirable characteristics. Now, again, all this is interesting to know, but very likely if you're doing digital design, even in an ASIC, right, a lot of this stuff is going to be something called standard cells, right? Does everyone know what a standard cell is? Okay, so what happens is, even in an ASIC, right, so there's multiple ways that you do a design in an ASIC, right? Oh, I shouldn't say more. There's 2 main ways of describing the design flow. It's called either standard cell or full custom. Right? Now you can have maybe somewhere in between, but anyway, the standard cell is essentially you write your and this is for an ASIC or a chip, you actually write your what you want the chip to do in Verilog. That's pretty standard. It's the same as FPGAs, right? The only difference is that instead of, sending the bit file to an FPGA in order to configure the switches in order to implement the logic in those lookup tables, essentially what happens is the compiler actually goes and you have a library which is usually written by the vendor, or I think it's some artisan. ARM doesn't. There used to be a company called Artisan that used to do them also, what you do is you've got this library, and what it does is when you're writing the Verilog code, and then after you synthesize it, what it goes and does, you say, well, I want an AND gate or an OR gate or whatever. It goes, grabs it, and instantiates it from that standard library. Right? So in most cases, even though we're doing this and this is super interesting, the probability that you'll be doing any of this kind of stuff is quite low, unless you're doing a full custom design, and that is like if you're trying to build a very, very fast processor, or you're maybe building analog to digital or digital to analog converters. They're probably the only major times that you would really care about this. But anyway, it's interesting, and at least you need to see it at least once in your life, right? Okay. Now, what we're going to do now is we're actually going to go through and look at how are we going to calculate this delay, right? Or the delay between these, and how are we going to generate delay models. Now, what we've done is we've worked out all these capacitors, and we've worked out all the resistance, and for a lot of times you can actually go through the process of trying to solve all this as differential equations. And if you're doing your control theory or system identification theory courses, usually you've learned about Laplace transforms, and you've gone through and tried to work out how to work out all those responses, right? Now, you might be able to do it if you're looking at one or two components or three components connected together. But suppose now you're looking at this processor. Suppose you're building a processor. You're lucky enough to be part of a project to build a processor. Now all of a sudden that processor has 10 billion, and that's billion with a B, right, transistors, right? All of a sudden trying to use your your Laplace transforms in order to solve all these 10 billion factorial, I think, coupled DEs is impossible. Just forget it, right? You just can't do it. So what we do, and what most tool vendors, example Cadence or Synopsys, is they usually come up with some crude approximations in order to be able to work out the delay, right? And this is where we're going to talk more about this RC delay model. And essentially what we're doing for these complex digital circuits is we're going to make some very rough approximations, and this is what Cadence or Synopsys does in their Calibre tool, or even DC compiler, is they use these stick transistor switch and series. They model a transistor as a switch in series with a resistor, and then they also estimate the capacitance. And Calibre, there's a tool, I don't know if you're all familiar with it, but there is a tool which does something called parasitic extraction, which essentially does what we're going to do here, which is it works out a way to estimate the resistance and the capacitance from your circuit in order to be able to work out the delay. Okay? So essentially what we're doing is we're modeling a transistor as a switch in series with a resistor, and what we do as part of this process in order to simplify the mathematics is when we've got a unit transistor, which is usually what we do when I'm referring to a unit transistor, is referring to the smallest transistor that you can actually build on your process. Okay? So if I said to you, you've got a 65 nanometer process, CMOS process, what's the smallest transistor that you can build? Okay, so it's 65 nanometers, right? So usually when someone tells you like 130 nanometer or 7 nanometer, what it means is that's the minimum feature length. And if you think about it, that's the minimum gate length, right? Now, it gets a little bit tricky when you're getting towards 7 nanometers because it's not actually 7 nanometers, it's a little bit larger, but then what they're saying is we do some tricks that make it look like 7 nanometers, right? But generally, when somebody tells you a geometry, they're actually telling you the minimum feature size. So when we're talking about a unit transistor, what we're actually saying is the minimum gate length transistor, right? And also the minimum, which also has the minimum constant diffusion length. So, as you can imagine, if the transistor is k times as large, what do we expect the resistance to be? R on K, right? Because all of a sudden you can think of the channel is now k times as large. The way, you can think of it as it's now, since it's k times as large or k times as wide, essentially what that means in terms of the effective resistance is 1 on k. Okay? Now, one of the approximations that we make in this process, which is sort of correct, is that when we define PMOS transistors, what we say is they're also a switch, but their resistance is twice as large. Right? And the reason for putting it twice as large is why? Can anyone guess? The mobility of holes is roughly half the mobility of electrons. It's probably 3/4, but for government work again, let's assume it's half. So therefore the resistance is twice as much, right? That's where that number comes from. All right. And what we're also going to do is we're also going to work out the capacitance, right? So we're going to talk about gate and diffusion capacitances. And usually what we say is if we've got a minimum size transistor, let's call the capacitance C, right? And this is just the size of the gate area, and and you've worked that out many times before. The thing is, if you've got a transistor which is k times as large, k times as much area, what do you expect the capacitance to be? You can say Kc, and then I'll ask you why.
When capacitor is parallel, the outer.
We wrote it. Okay, yes, I've written it somewhere. Remember, it's C. Capacitance is epsilon A on D. If you're 10 times as large, therefore A is 10 times as large, so therefore your capacitance is 10 times as large. All right, good. The same thing applies for your substrate.
Sorry, just quick about this. Isn't A like k squared larger?
No, but here I'm talking about area.
Oh, okay.
Right, so... but it's a good question. I like it, but yes, usually what I'm trying to do is make everything linear, right? And that's what people do. Try to make everything linear, so therefore it becomes. But yeah, generally, what you've got is you try to keep the minimum gate length, and then you change the width of your device, right? Rather than changing both the length and the width, right? Because you change the length, the device slows down, right? Transit frequency is 1 on length of the gate. All right, so we've also got the substrate capacitances. Now, just as a rule of thumb for everyone, the capacitance for a CMOS transistor generally is about 1 femtofarad per micrometer, and roughly for a 65 nanometer process, which is what most people would use if they were doing not particularly advanced, but cost-effective digital circuits, you'd use a 65 nanometer process. So that's why I've actually put this value down here, right? If you're doing a 65 nanometer process, the mask sets probably cost you $200,000, so you can actually afford it. If we went for a 7 nanometer process, the mask set's $25 million, and you'd be very likely to be involved in that kind of work. So what I'm doing here is now drawing out the equivalent circuits for both the NMOS and PMOS devices, right? And essentially, if I'm saying if this device is K times as large, what I've got is the resistance is R on K, the substrates, the two substrates, source to base and, drain to base and source to base capacitances are K and C, and the gate capacitance is gate on C. And likewise, for a PMOS, everything's the same except for the fact that the resistance here is 2R on K. Okay? Because we said, remember, it's half as fast, the melody is twice as half that of the NMOS device, so therefore we're approximating the resistance as being twice as large. Yes? Was there a question?
For the PMOS, is 2R on K or 2R on 2K?
2R on K. That's me not being able to write. 2R on K.
So what's wrong for the
Sorry.
bottom one?
Sorry, KC. Yes. Okay, thank you. Thank you. So, 2R on K, KC. Thank you. All right. Okay, how are we doing? We've still got time. Good, good. So what I've done here is essentially have gone through the process now of actually drawing this equivalent inverter circuit. What equivalent inverter driving another inverter. All right, why have I got C and 2C here? Yeah, and here what I've got is K equals 2, and I've said the size of the size of the PMOS device is twice as large, whereas the NMOS device are making it 1x as large, right? I just wanted to point that out. Rather than the resistance would be is still R because I've got it twice as large. Right? Sorry. Okay. All right. So now let's draw the equivalent circuit here, like the and we've got these two capacitances, all the capacitance that we need to include. Now like we talked about previously, these two are non-switching capacitors, so we can ignore them. So this is the equivalent circuit that we need to deal with. And when we're going, essentially from a transition from 0 to 1 at the input, which is at the output, we're doing 1 to 0. Essentially, what we're driving is 6 units of capacitance, 1 unit of resistance. Okay, and then you can use that to actually work out what your response is going to look like. Right, so there's 2, 2, 1, 1, so that's 6, 1 unit of resistance. The switch is open here, so I don't have to consider what's happening in that resistor. Okay, so therefore this tells us how quickly the output will change from a transition from 1 to 0, right? So you can think of it as, you can do your Laplace transform or whatever, and you can say, well, if I set this, and if this was initially voltage 1, how quickly does this discharge? Can anyone remind me, if you've got this circuit where you had charged, you can think of it as if you charged this capacitor to a particular voltage, how quickly would it discharge? Usually. Suppose the capacitance was 1 unit. How quickly would it discharge? What's the time constant? RC. 1 on RC, right? So in this particular case, it's 1 on 6 RC. Right, that's its time constant. Okay, and if you're going to work out the propagation delay, how would you work out the propagation delay? So let's, you know, this is where we go back to our Laplace transforms. I won't go too much into details because I know our department loves systems and signals and systems, so you've probably seen these Laplace transforms 100,000 times. So I'm not going to focus too much on it, rather than to say, well, if you've got this